Okay, so for this next problem, what I want to do is find the Laplace transform of t. Now, this Laplace transform of t is going to be a function of s, so it's not uncommon to see the function of s notation after that. Now again, the definition of our Laplace transform excuse me, is the integral from 0 to infinity e to the negative st times f of t dt. So we're just going to find the Laplace transform of t using that definition. I'm going to plug it in. And we have to take this integral. T times e to the negative st dt. You've seen this before in a previous calculus class. And if you remember it, you may not actually like it very much. It is an integration by parts problem. With u equals t, in dv, which is the other piece that you have to pick out, e to the negative st dt. Now if we take a derivative of u, du is dt, we take an integral of dv, and we get v is negative 1 over s e to the negative st. If we plug all this into our formula for integration by parts, we get uv keep in mind we had limits on this integral, so we're going to have to evaluate this from 0 to infinity. And the other part of our integration by parts formula is the integral of v du. So negative 1 over s e to the negative st dt. Again, we have limits on that integral, so we're going to have to do another improper integral taking the limit as b goes to infinity. I'm going to integrate first. I'll do a little bit of simplification here. We know that we're going to evaluate this from 0 to infinity. I'll write that in a minute. If we integrate, notice we already have a negative and a negative. That's going to make a positive, but when we integrate, we're going to bring out a third negative. And we're also going to bring out another factor of s. So we're going to have a minus 1 over s squared, e to the negative st. All of that we're going to want to evaluate from 0 to infinity. Of course, we can't just plug in infinity, so we have to take the limit as b goes to infinity of negative t over s e to the negative st minus 1 over s squared e to the negative st from 0 to b. Plug in our limits. Again, we're plugging b in for t because t was our variable of integration. We're going to subtract what we get when we plug in 0. Of course, in this first term, we're just going to get 0. I'll write it out. Okay, so we want to take limits as b goes to infinity of those first two terms. These last two are pretty obvious. We have a 0 here, and we have a 1 over s squared here. So we want to limit as b goes to infinity of negative b over s e to the negative sb. One way to think about this is to write it out like this, with the e to the sb in the denominator. Now just looking at that, b is increasing. B is getting big very fast. The numerator is going to get big, but the denominator is going to get big even faster because it's an exponential function. Now again, just like in the last problem, we're assuming that s is positive. The more technical way to do this, to find this limit, is to use L'Hopital's rule. So you would plug in b goes to infinity, and you get infinity over infinity, which is an indeterminate form. You would use L'Hopital's rule. You take a derivative of the numerator with respect to b. You get -1 over the derivative of the denominator with respect to b is an s squared e to the s b b. And now that limit obviously goes to 0 because you have 1 over infinity. This limit on the right hand side here is a little bit more obvious. I think it's a little bit more clear that that limit is just 0 because there is no numerator. You plug in b as b goes to infinity, and we get 1 over infinity, which just goes to 0. But I'll write it in anyway. Okay, so we just made an argument using L'Hopital's rule that this limit here goes to 0. We also just made an argument by basically plugging in b as b goes to infinity, that that term goes to 0. Our third term went to 0 because we plugged in 0 and it went away. Our fourth term, the only non-zero term, is just 1 over s squared. So what we just found was the Laplace transform of t, which again is a function of s, so you can use that notation. It's just 1 over s squared. Now we can continue to find Laplace transforms of functions just using the basic definition of a Laplace transform. Of course,